Okay, so this video is going to be all about fluids that are moving. And so we're talking about water moving in a duct. So this is kind of like our, we've got a small little hose and it's emptying into a big hose. And so what we're going to do is we're going to find out that our fluid is going to go really fast where it's skinny and then slower when it's fat. And that kind of makes sense. It makes sense when really makes sense when we reverse the direction of the arrows. Because this is kind of how our power washers work. We have our water in our big hose, and then it comes out through a little opening, and it comes squirting out the end. Okay? So you've experienced this when you've put your finger over the end of the hose, and then, if you don't have your finger, the water comes doo-doo-doo-doo-doo out, and then once you put your finger in, it comes squirting out, and you can squirt it for miles because it's coming out faster. And so how fast it's going is really a reflection on the cross-section area. Okay, so it's the areas of the two parts of the pipe that it's going through. And so the equation we use is that the area times the velocity is equal to the area times the velocity. So you'll see if we have a bigger area, we're going to have a smaller velocity. If we have a smaller area, we're going to have a bigger velocity. See? That's easy, right? So you're going to use this anytime a tube gets smaller or a tube gets bigger. Now here's a very interesting thing that happens though, is as a fluid is moving faster and faster and faster, the pressure actually decreases. Okay? So the faster you're going, the actual pressure, the static pressure that you feel actually decreases. The total pressure in both areas is going to be the same, but we have two different kinds of pressure, and we're going to talk about those next. Okay, kind of the two types of pressure we have are static pressure and dynamic pressure. Static pressure is the pressure that is pushing on the sides of the walls. So that's what's pushing out of the walls. And then your dynamic pressure is the pressure of the fluid itself that is moving inside. So that's the pressure of the moving fluid, and they all come together to form the total pressure. And the total pressure in a system is a constant. So the total pressure is whatever the pressure of the outside is. So that could be like air pressure. And a lot of times this term will cancel out because it'll show up on both sides of the equation. Plus your static pressure, plus your dynamic pressure, and that's always going to be the same. So that's going to equal your outside pressure plus your static pressure plus your dynamic pressure in a different area. But the total pressure in the two areas is going to be the same. Okay, so remember we said that when the fluid was moving faster, the pressure was less. Actually, the static pressure is what ends up being less. And remember, that's the pressure on the sides of the walls. And so as your fluid's moving faster and faster and faster, your dynamic pressure is going to increase, which means that your static pressure has to decrease. So there's less pressure actually on the sides of the walls because the total pressure has to remain constant. So this is very much like conservation of energy, and if you look at it, our equation is going to look very much like conservation of energy also. So let's get to that. So our total pressure equation is going to be the pressure of the outside, wherever it is. So we could be talking inside the house, outside the house, because we do have a problem in our pretest where we've got wind blowing across the roof, and so we have a pressure inside the house and a pressure outside the house because it's different because we've got moving air. So where do you think the pressure is going to be smaller? Because remember, the total pressure outside has to equal the pressure inside. So inside pressure is actually going to be bigger, and this is why roofs fly off of buildings during tornadoes. So it's going to equal our pressure, whatever that pressure is, plus rho GH. Okay, so this is our static pressure depending on our height. So this depends on our height. So when we have a vat, that's, remember we were talking about the pressure down here at the bottom was rho GH. Okay, that's this pressure. But if I'm part way down, I've got this pressure. And if I've got a hole in the wall right there, now I've got some velocity. I've got some water squirting out there. And that's going to be 1/2 rho v squared. If you really, really, really look at this, okay, rho is kind of like its density, so it's kind of like mass. So mass times gravity times height. Ooh, what kind of energy is that? That's like potential energy. So it has the potential to make the water squirt out. 1/2 rho v squared, that's 1/2 like mass times velocity squared. It's not mass, remember it's density. But that's the velocity of this water as it comes out of the tank. And so this is going to equal the situation in the other place, equals whatever the pressure is plus rho GH plus 1/2 rho v squared. So we can use parts of this equation because sometimes there's no change in height, so that would cancel out. Sometimes nothing's moving, so our velocities will cancel out. Okay, so if there's no change in height and no change in velocity, guess what? There's no change in pressure. How about that? So, easy enough. So, look at the house question on your pretest, and it's basically asking you what's the change in pressure. So you're just going to set your pressure outside, plus now you've got this moving air on top, so you've got moving air, 1/2 rho v squared is equal to the pressure inside. And if you want to find the change in pressure, or the pressure difference, you're just going to put both of your p's on the same side of your equation. So, not so bad. Go try those problems. We'll talk about them tomorrow. Good luck. Bye-bye.